Hello, welcome to an introduction video to the Safeti 3D Explosions module. In this presentation we're going to just talk through some of the background basics of the capabilities of the software and then run through a brief demonstration of the software. So we're going to have first a look at the standard capabilities of FAST and Safeti for performing explosion calculations. The standard functionality of Safeti I'll refer to as the 2D damage zone method. So let's start by looking at FAST. So in FAST, at the most basic level, you have a container, some kind of storage or process equipment containing flammable material. You have a loss of containment, and then through the dispersing cloud of flammable vapor or gas, you'll have ignition. And that will lead to some kind of overpressure hazard zone. And ignition occurs at regular intervals through the cloud, leading to a range of possible results. The explosion models available in FAST are the TNT, TNO multi-energy and Baker-Strelo explosion models. So this approach, you need to know what the flammable cloud consists of, so how has the dispersion behaved under different weather conditions and the different discharge models that can be run, and then what the ignition interval is, which is a 10-meter spacing by default. And FAST will help you work out where the worst case explosion occurs, so that's where the overpressure level of interest has the largest blast radius and reaches the greatest distance. So looking at this in a bit more detail, let's have a look at what the inputs are required for this approach in FAST. So FAST needs to know how much flammable mass is available for an explosion, and this is automatically calculated by the discharge followed by dispersion calculations. The ignition location, now that's either this default 10-meter spacing, which you can edit, or in each individual release case you can specify a late ignition location. The TNT model, if we're to use that method, requires an explosion efficiency value, which is 10% by default, 10% of the heat of combustion of the flammable material. And then you specify whether there's a ground or air burst. It's a fairly simplistic model, only those two inputs required. The TNO multi-energy model, for that we need to define a confinement strength and a confined volume. So of all the flammable mass available in the atmosphere, what fraction of it, either by fraction or volume, is going to be involved in the explosion. And finally the Baker-Strelo model, where we get a little bit more assistance than the multi-energy model, where we work out the blast strength based on a material reactivity, the flame expansion, the dimensions through which it can expand, the obstacle density, and the reflection factor. And then the obstructed volume, like the confined volume, how much of the cloud is involved in the explosion. So let's have a look at the outputs provided by FAST. We receive information about the blast radius created from each explosion location source, the flammable mass included in each explosion, and we get details in graphical form and in the summary reports of the worst case explosion, so the radius of the blast when the overpressures of interest reach the greatest distance. For the multi-energy model we receive information about pulse duration, and the Baker-Strelo model we receive information about impulse. So here's an example of worst case explosion results for a range of overpressures versus distance. And here's from the reports information about the 10-meter interval steps, the flammable mass involved in the explosion, and the blast effects were felt at a certain distance away from the source. So let's look at Safeti. Using Safeti with the 2D damage zone method, we start with a process vessel containing our flammable material, which undergoes dispersion. And in Safeti, in the risk analysis calculations, we rotate that release through all the directions of a windrose, each direction having a different likelihood probability assigned to it. And in Safeti we also care about the likelihood of ignition, so ignition sources are drawn on the map. When we have interaction between an ignition source and flammable concentration, we'll experience ignition. The explosion model in Safeti gives us results of two damage level radiuses, so for heavy blast damage and light blast damage. This will occur accompanied by a flash fire, which is governed by event trees. Ignition will occur again, at other locations where flammable clouds and ignition sources intersect, and we'll get more blast zones and flash fires. And this will keep occurring all the way around the windrows and at different time and distance steps throughout the cloud. Of course, this has just been simplified as busy as the diagram looks. The model used to achieve this is called the Wickham model, and the inputs required in general are the flammable cloud and some form of ignition source. But let's look at that in more detail. So here are the inputs required for these explosion calculations performed in Safeti with the standard 2D damage zone method. So flammable mass in the cloud is required. Of course, that's provided by the dispersion calculations. Ignition source locations need to be specified by the user. Weather direction probabilities are to be specified. And also event-free probabilities, so the split between immediate and delayed ignition, and also the fraction of when you experience flash fire, when you experience explosion. Default values are provided for all of these. The Wickham explosion model uses two damage level coefficients which are tuned to represent heavy and light blast damage, and default values for these are provided, but they are editable. The outputs from the Safeti 2D damage zone method explosions are, of course, the contribution of these explosions to the risk results. So not actually seeing them directly, but seeing their explosion contribution in terms of probability of death in your individual and societal risk. Details of the blast are provided in the hazard zone report for the immediate ignition event, but no details of delayed ignition outcomes, so as we saw in the previous animation, are produced, other than in diagnostic files, so they are available but they're not produced graphically or in a report. So just some notes about Safeti's capabilities and explosion modelling here. There's no consideration of obstructed regions and what part they play in explosion sources. Explosions can occur anywhere that there's flammable mass and ignition. There's no support for determining blast strength. It's only governed by the flammable mass involved in the cloud using the Wickham method. And using the Wickham method, all of the flammable mass is used in the cloud, so everything between the flammable limits, not just a fraction that's in an obstructed region. There's also, importantly, no consideration of the vulnerability of targets. So, other than the broad consideration of people indoors and outdoors and their exposure to heavy and light blast damage, there's no more detailed rigour applied in terms of vulnerability. And if we consider fast, then when working with the multi-energy model, there's no assistance given. The confinement strength is a input only. There's no help in choosing that number. So let's now look at what the 3D explosions module can do. So here we have a fairly simple arrangement where we have a vessel, a cloud, an instantaneous cloud that's been released that's going to drift in the wind direction towards an obstructed region and some kind of target, a building perhaps. So at this point, at time step 1, the cloud has no contact with the obstructed region and no explosion is occurring. If there is ignition of the cloud at this point, there will just be a flash fire and an unconfined explosion. Time step 2, the cloud is drifted further downwind and we've now got some intersection between the obstructed region and the flammable cloud. And at this centre of the overlapped area is the centre of a blast. And you can see the blast effects travel a certain distance away from the source of the explosion. Outside of the obstructed region, we will experience a flash fire. Moving on to time step 3, and you can see now the clouds drifted further downwind, and we now completely envelop the obstructed region, which gives rise to a larger blast radius. And you can see now the target, the building, has been affected by this blast. Moving on to time step 4, we get another smaller explosion, but of course we're moving towards the target. Time step 5, there's no explosion, but the building is now involved in a flash fire. Each of the explosion outcomes we just saw through the animation represent parallel branches on a cascading delayed ignition event tree, so effectively they're all happening in parallel universes. Had the first ignition occurred, there'd be no cloud left to burn. And the final time step, we have no interaction with the building at all. So now the cloud has drifted completely downwind. With a low probability of ignition throughout your plant, the cloud reaching this greatest distance becomes more likely. So, as we saw in the previous animation, the components involved in an explosion using the 3D explosion method are the release containment vessel, the cloud in one of its weather directions, an obstructed region, an ignition source, and we also need to consider the receptor, which may have specific vulnerability. So this arrangement can give rise to a fairly complex situation where we have several process vessels in our plant, several obstructed regions, and we may be considering one particular sensitive target. We consider dispersion through all the weather directions that are possible for all of our releases, and the model needs to consider all of the potential explosion sources resulting from this arrangement, and we assess the impact from each of those explosions on the receptor, keeping a log of all of the potential interactions and impacts that give rise to damage at our point of interest. Each of these explosion outcomes hitting a receptor, such as a control room or a warehouse or the site boundary, has a different likelihood of occurrence, and the traditional way of representing this is in the form of an exceedance curve. So for those familiar with traditional QRA, this is analogous to an FN curve where we have frequency of experiencing a range of events. On this graph it's side-on overpressure. So at a control room or a warehouse in a particular case study, we have this full range of potential explosion overpressures that are possible with decreasing likelihood as we move down the y-axis. So different fuel sources, different dispersion directions, different ignition sources and obstructed regions gives rise to a range of potential explosion outcomes that all have different likelihoods. So let's see a demonstration of this in Safeti with the 3D explosions module available. So this is Safeti. It's arranged with a tree on the left with all of our inputs organised onto tabs, and an area on the right where we'll see our map and reports and graphs. So in this particular study we have a range of propane storage tanks, which you can see here over on the map. These green dots represent the north, middle and south propane storage tanks, and from each of these we have a range of potential releases, small, medium and large leaks and ruptures in each case. The set of dispersion and explosion calculations will be conducted for a range of different weather conditions. So here we have a folder of daytime weathers and nighttime weathers. So we have a stability and wind speed assigned, and also if I double click the folder here, you'll see that the direction and condition probabilities are assigned in a traditional windrows table. So some weather directions are dominant and some are less dominant. So over here on the map, if I just switch off some of the larger images in the background and zoom in, you can see we have a process plant described with these pink regions sitting on top, and these are the obstructed regions. So we have a number of calculated strength obstructed regions drawn onto the map and certain properties assigned to them. So we'll just take a moment to discuss what an obstructed region is for a moment. So the form of a, for example, multi-energy explosion model contains a flammable cloud which experiences ignition, and you get a hemispherical blast that propagates out in all three dimensions, or through 2 dimensions as well. So there's a peak overpressure that occurs, and then you get decay away from the blast center as you travel away from the cloud. The peak overpressure is a function of the obstructions. There are 10 confinement strengths that are defined, and this set of correlations is used to work out what's the peak side on overpressure and what distance does overpressure reach as the blast wave decays and travels away from the explosion source. In FAST, these numbers from 1 to 10 are inputs to the TNO multi-energy explosion model. In Safeti, there's further support for determining which blast strength should be used, and that comes from the 1995 work, the game formulation. So here we see a correlation that links the volume blockage ratio of the obstruction, the flame path length, the typical diameter of the objects in the obstruction, and the laminar burning speed of the material. So when a blast wave can expand through 3 dimensions, we use this form of the equation, and through 2D expansion, we use this form. So going back to Safeti, if I choose one of these obstructed regions, either from the tree or from the map, pick this here, pick this calculated strength obstruction and say edit, you can see that the inputs relate to the game correlation methods that are used for determining the blast strength. So I choose a degree of expansion. Which of the 2 equations am I going to use? What's the volume blockage ratio? And what's the typical diameter of the objects inside this obstructed region? And then I can either specify a flame path length or have it calculated from the shape that I've drawn on the map. The laminar burning speed comes from the material that is dispersing through the atmosphere and into this obstructed region. So let's take a look at the arrangement of the objects in our study. So switching the aerial photo back on and saying fit all, here I have a plant around an area near the coast with public population nearby. If I zoom in, you can see the green dots represent my 3 propane tanks. The red dot here is an ignition source. So remembering what we saw in the previous animation, each of these propane vessels can have a loss of containment. The flammable cloud can drift with the wind in a range of directions according to the weather probabilities and potentially drift into these obstructed regions. If we have the presence of flammable gas or vapour, an ignition source and an obstructed region, then we will get an explosion. And in this study there are a range of failure scenarios, many weather directions and lots of obstructed regions, even for a simplified study. So that's a lot of data to process. The receptors of interest are represented by these small blue dots here. One is located, if I just click it, it tells me that's a risk ranking point located at a warehouse. And here in the south there's another blue dot, that's a risk ranking point located at a control room. And those control room and warehouse buildings have been specified on the map with a certain level of vulnerability and a certain level of occupancy. So let's take a look at some of the results. So over here on the Run Rows tab, which is our run control, we can see the traditional, of course, FN curve, which shows us the frequency with which a statistical number of fatalities may be experienced. We can also view the traditional location-specific individual risk contours, which will be displayed over the map. And of course this is by default taking account of all of the potential hazards, so jet fires, fireballs, pool fires, toxic impact, things like that, depending on the inputs to your case. And you see the results as a series of ISO lines through effectively a risk array, so a set of risk contours around your plant. Now, to account for the more complex calculations that are performed using the 3D explosion method, a new reporting format has been produced. Because of the large number of explosion outcomes that need to be logged to analyse risk to occupied buildings effectively, this new extended risk reporting tool was introduced. I've generated the database sitting underneath it and launched the extended risk reporting tool here. So there's a large range of potential risk results that I can see here in the extended risk reporting tool. I'll start with just a simple view of the risk ranking point results. So if you recall, we had 2 blue dots on the map, one at a control room and one at a warehouse. So for those particular points of interest, Safeti logged every single explosion blast that reached those 2 blue dots on the map effectively. And we can see those in the form of a side-on overpressure exceedance curve, as we saw in the slide earlier. So there's a frequency of exceeding these overpressures along the x-axis. And you can see the blue line represents the control room, the red line represents the warehouse. And each of the points on the curve is an independent explosion event. So I can view explosion details for these particular curves, and I'll see a table containing useful information. So here I've grouped things by model name, which is the release case, and then I've grouped by obstructed region. So if I look at the beginning, you can see I've got some large leaks. The dispersing cloud has drifted into the one-story main building obstructed region, and that's given rise to a range of different potential explosions depending on the specific weather direction and the time step that the cloud was going through. So the exceedance curves and their drill down capability are very powerful tools for capturing a large log of information for details at a specific point. An alternative way of viewing explosion results is to use a risk contours approach. So for this 0.3 bar overpressure risk contour filter set that's been created, I'm going to look at a multi-risk level view. So let me just, while that's being generated, I'll jump back to Safeti and show you what this means. So here on the map tab, a range of escalation vulnerability sets have been created. One of them is 0.3 bar escalation. So this has been developed whereby for obstructed explosion vulnerability, rather than defining the properties of a building such that there's a variable relationship between probability of death and overpressure, it's been set up so that 0.3 bar overpressure gives rise to fraction of probability of death of 1. So what that results in terms of risk contours, is a log in the risk array every time 0.3 bar overpressure is experienced. And of course with that we capture the frequency. So here we have contours around our site of these frequencies, you can see here in the legend, of experiencing 0.3 bar overpressure. On that basis, and knowing the vulnerability or the capability to withstand certain overpressure levels, you can use it to assess where buildings should be located and which buildings are currently at risk. This has been a brief introduction to the explosion modelling capabilities of the Safeti 3D Explosions module. If you have any questions or would like to get in touch, please contact us at dnv.software@dnv.com. Thanks for watching.